Hello everyone, this is Manabu Tsukada from the University of Tokyo. Thank you for the opportunity to talk in this wonderful conference. Today, my talk is titled Cooperative Automated Driving using V2X. In this talk, first, I will talk about the connected cooperative and automated mobility trend advancing in Europe. Next, I will explain the technical standards, especially in Europe, and talk about Autoware, a popular open source automated driving software. After that, we will introduce three recent research works in our laboratory on V2X assisted automated driving. Let me begin by talking about the intersection of the connected car, cooperative ITS, and automated driving. This concept is known in Europe as connected cooperative and automated mobility (CCAM) and in the US as connected and automated vehicles (CAV). The connected car is a part of Internet of Things. The expansion of Internet is connecting things that were previously not considered as computer to the Internet. In the world, about 35% of cars sold in this year are connected cars, and in Japan, 75% are connected cars. Cooperative ITS is a system in which vehicle, roadside, central servers, and pedestrian terminals share information to make road traffic safe, efficient, and comfort. Cooperative ITS is a concept that has emerged mainly in Europe as a public-private ecosystem for ITS applications that realized safety, efficiency, and comfort. In this presentation, we will discuss this CCAM with our recent research work. CCAM is an initiative that is being proposed in Europe. Horizon Europe is the EU's essential funding program for research and innovation with a budget of 95 billion euros. In it, CCAM has announced 10 calls for the project, totaling 123 million euros for this year. This shows the importance of CCAM on research and development themes. The keywords were connectivity and cooperation, cybersecurity and resilience, large-scale demonstration pilot, human-machine interface, explainable AI and trustworthy AI, and more. The wireless media that connect vehicles are conventionally referred to as vehicle-to-vehicle (V2V) and vehicle-to-infrastructure (V2I). Later, vehicle-to-pedestrian and vehicle-to-network were added, and now we call it vehicle-to-everything (V2X). Just as your mobile phone has two communication modes, Wi-Fi and cellular, V2X also has two modes, dedicated short-range communication (DSRC) and cellular V2X (CV2X), where DSRC is like Wi-Fi and CV2X is like cellular. Since 2010, DSRC started to be developed, verified, commercialized, and deployed. In many countries, DSRC use a 5 GHz frequency, and IEEE 802.11p exist as a specifications. 11p is used in the United States and Europe, and the profile for the EU is called ITS-G5. In Japan, 700 MHz and a 5 GHz band is used as DSRC. The 5 GHz is used for the electric toll collection system known as ETC. These communication specifications have been standardized by IEEE, ETSI, and ARRIVE in US, Europe, and Japan, respectively. CV2X came later and now being standardized by 3GPP that has been developing technical specifications for 3G, 4G, and 5G. In release 14, the LTE V2X specification was added, and after release 15, the V2X specification for 5G will be added. V2X supports communication between terminals called PC5 or side link, which does not require a base station in addition to the conventional communication from vehicle to via a base station. Cooperative ITS has traditionally been designed on the premise of DSRC. Still, with the advance of cellular V2X, the access layer technology may be replaced, or perhaps DSRC and cellular V2X may be used together to support ITS safety applications and non-safety applications. IEEE, ISO, and ETSI are working on designing the network layer, transport layer, and facilities layer. Even though access layer is being replaced by cellular V2X, the upper layer will be reused. This document was borrowed from Qualcomm's presentation. Qualcomm is promoting cellular V2X, so this is the thinking of the cellular V2X group. This is a roadmap for the technical elements of CCAM as envisioned by the European Commission. It is a roadmap for cooperative ITS, connected car, and automated driving for the next 25 years until 2045, divided into 4 categories from day 1 to day 4. Day 1 is the beginning of awareness, where the main objective is to share the information that vehicles have. The specifications for this have been standardized by ETSI, European Telecommunications Standard Institute, and commercialization has begun. The ETSI specifications, EU stand for European norms, TS for technical specifications, and TR for technical reports. They are more important in this order. ETSI standardized cooperative awareness message CAM to share the location of the vehicle, a decentralized environmental notification message DENM to share the traffic information, and a database called Local Dynamic Map stores the information obtained from these messages. Day 2 started this year, 2021. I share what I see, it says. An effort is underway to standardize message for sharing sensor information. This message is called Collective Perception Message, CPM, and specification and analysis are being discussed as TS and TR respectively. 5G will be introduced in terms of connectivity, and automated driving demonstrations will be carried out in limited areas. Day 3 will see the start of cooperation. We share our intentions, it says. As far as we know, standardization has not started yet, but research on CAM extends the future path. Later in this presentation, we will talk about the research on future path sharing. On day 4, fully automated driving will become widespread, and automated vehicles will coordinate all operations with each other. We will start discussing a message for this called Maneuver Coordination Message, MCM. From this slide, we will talk about automated driving. Automated driving replaces the 3 human behaviors of see, think, and control with sensors, computers, and actuators. The figure on the right shows the level of automated driving from level 0 to level 5, created by Society of Automotive Engineers. The first run is a maneuver, followed by monitoring, fallback performance, and limitation. Until now, the mainstream of level 2 has the system automatically steer the vehicle in a specific scenario, but the human monitors the driving environment. Today, the demonstration experiment is level 3, in which the system performs steering and monitoring of the situation under specific conditions. However, suppose the vehicle deviated from the specific conditions or go out of the area. In that case, human intervention will be required as fallback performance. Level 4 and Level 5 are called fully automated driving, and the difference is whether there are restrictions on conditions and the area or not. Many organizations are developing various autonomous driving software for fully automated driving. Still, as far as we know, there's two open source software that are Autoware and Baidu Apollo. Autoware is a project started by Nagoya University in Japan, and our university commits to its research and development. Autoware runs on Ubuntu Linux on a general-purpose PC. Autoware uses RobotOS, a popular software for controlling robots as a middleware, and Autoware provides the function needed to realize automated driving as a set of application packages. For example, 3D localization, 3D mapping, sensor calibration, sensor fusion, object tracking, path planning, path following, and more. Since 2018, Autoware has been developed in a non-profit organization called Autoware Foundation. Discussions and development are carried out democratically. Currently, as the list shows, premium members, industry and government, academic and non-profit members, and affiliated organizations participate in the foundation. The University of Tokyo is also a member of this foundation. Here is an overview of what happens when Autoware is run in a city. Right now, a vehicle is West Shinjuku, Japan, in a crowded city center. This image is borrowed from Tier4's experiment in 2020. Autoware mainly uses camera and LiDAR as sensors. LiDAR measures distance to a target by illuminating the target with laser light and measuring the reflect light with a sensor. This is active measuring, which also works well at night and is strong to light conditions. On the other hand, it is weak against bad weather conditions. This point cloud is used for localization and object detection. Autoware has a pre-made map of the road you need to drive on. The map is database for the vehicle. It provides information about the road, the intersection, lanes, road edge, center line, and signal. There are two kinds of map, point cloud and vector map. The point cloud is used for localization by scan matching. The vector map is used for understanding the road network. Autoware provides the detection of surrounding objects. Vehicles and pedestrians are visualized as boxes and pillars. The most used algorithm of object detection is clustering of the point cloud. Next is prediction. Autoware predicts the movement of vehicles and pedestrians. Autoware shows the future trajectories visualized as lines and points, commonly called as waypoint or future path. The vehicle is predicted by the road movement model. Pedestrian is predicted by the free space movement model. Autoware decides the action for driving to the destination. This example, the vehicle in front is an obstacle. Also, traffic light and intersection is a factor for slowing down. Autoware is used for few hundred of field operation, demonstration, and experiments. This video shows the field operation in Nishi-Shinjuku, Tokyo. The signal is red, so a car is waiting. We see a lot of pedestrians crossing the street. A car is coming along the predicted path. The light turns green, and the car in front moves forward. The Autoware car is following. The three works we will present today are Autoware V2X extensions to support cooperative driving. The figure below is divided in upper and lower part. The upper part represents the functional blocks of standalone automated driving software. This functional block is a general processing flow that is not limited to Autoware. First, perception is performed using the map and sensor as an input. This includes object detection and object tracking. Next, prediction is performed to estimate the future movement of the object. Then, based on this result, planning is performed to control the vehicle. The first work is the research work to support perception with cooperative ITS. Next, B is the research work to define the future trajectory and future paths and perform cooperative planning based on this. Finally, C is the research on maneuver coordination. If you are interested in each of these studies, please check out the article and presentation video in open access. First is cooperative perception we presented in VTC4 last year. Traditional ITS relies on communication with the onboard unit and roadside unit. The traditional cooperative ITS could not accommodate vulnerable road users, VRUs, which means pedestrians and motorcycles, because they do not have onboard unit and do not connect to the vehicle or the road infrastructure. Now, people recognize that how VRU can be incorporated into the framework of cooperative ITS will be the key to their deployment. Cooperative perception is a framework for sharing observation data from sensors installed in vehicle and road infrastructure. In the example at the top, the pedestrian data observed by the sensor installed in the white car and roadside are sent to the red cars. Sensor data sharing can be classified into three categories depending on the instant of occurrence of sensor fusion. In the raw-based, low-level method, the raw data from the sensor is shared. In the feature-based, middle-level method, pre-processed data such as bounding box from a vision-based object detector are shared. In the object-based track-level method, the position information of the object in the global coordinate are shared. Of the three methods, the object-based method is most realistic for widespread use, considering the current performance of wireless media. For this category of method, the SCCPM specification is under development. Our laboratory has been working on ProxyCam, which is a CAM-encoded cooperative perception method. This method is compatible with products that can receive CAM that currently exist in the market. Here is an overview of ProxyCam. First, the sensors on the roadside detect blue target cars, estimate their positions and status, and create a database on the roadside. The data is then encoded into a standard message for the region. Then the roadside transmitter sends the message instead of the target vehicles. The red car will then be able to recognize the presence of target vehicles. Similarly, cars with sensor and transmitters can send ProxyCam in the same way. We have tested whether cooperative perception using ISO ETSI standards can support automatic driving. First, we extended Autoware, which was developed as a standalone automated driving software by V2X. We designed a new Autoware V2X by combining OpenC2X, an open-source ETSI-compliant software, with Autoware. OpenC2X implements the ITS station architecture, which consists of a set of ISO and ETSI standards. It also has the network layer and facilities layer stack that we need. In the network layer, geonetworking for vehicular network is partially implemented, as well as IPv6. In the facilities layer, CAM, DENUM, and LDM are implemented. In the standard specification, the facility layer also includes CPM. We design a system in both vehicle and roadside unit. In the design, host realize perception. In contrast, a router takes charge of cooperative ITS function. Put differently, OpenSys and Autoware operate in different nodes rather than being deployed in one computer. This design was chosen since a vehicle and RSU typically include some dedicated computer necessitating external connectivity. As a case in point, dedicated computer could be a vehicle for navigation, mapping, and driving log. Similarly, an RSU could have separate computers serving in traffic monitoring system, edge servers, and signals and signage. For this reason, it is better idea to ensure that a router manages all the nodes' external connectivity as opposed to extending all the nodes to have external connectivity include the antenna. A key difference between RSU and vehicle is the equipment of wired connectivity and mobility. The vehicle's controller area network can gateway help gain control over steering, braking, and acceleration. In contrast, the RSU has wired connectivity to the internet as well as roadside networks. The figure provides an overview of our AutoSys architecture. C++ language was used to develop AutoSys through the extension of OpenSys and Autoware. The source code can be accessed at the URL. Since Autoware and OpenSys have overlapping self-positioning functions, AutoC2X uses Autoware's self-positioning data with higher accuracy. In addition, since Autoware's coordinate system and OpenSys's coordinate system are different, they are mutually transformed to exchange data. After initiating a system, Autoware reads the 3D map and began receiving the sensor data. The system localizes the echo vehicle and then gets the neighboring object detected. OpenSys sends the self-location as a CAM and neighbor object location as a proxy CAM. Simultaneously, the LDM stores the data. Upon receiving our CAMs and proxy CAM, the OpenSys router extracts the information related to the neighboring object from messages before storing it in the LDM. OpenSys then transmits the object's coordinates to Autoware. Finally, the object-related data extracted from the V2X communication gets visualized in Rviz, losses visualizer, the feedback to the planning module in our future work. We verified this implementation at Crossroads in Hongo campus in the University of Tokyo. This figure shows the experiment. In the experiment, we set up identical set of routers and hosts, antennas and radars on the roadside and in vehicles, respectively. The experiment was tested indoors and in the field with same equipment. According to Japanese regulation, Wi-Fi 11G ad hoc mode is used for the test. The video shows a field test. The onboard sensors recognize objects around the car. The roadside unit sends remote object via V2X messages. The object is visualized as a square centered on the transmitted coordinates. In the indoor test, we measured the message latency. The total delay T is expressed as the sum of TPC, THR, TRR, TRH, where TPC signifies the delay in Autoware, and THR, TRR, TRH denotes the transmission delay from the host to the router, between routers, and from routers to the host. TPC includes the processing delay in Autoware on the clustering the point cloud, detection, and localization of the object. The top figure shows the result. As the As in the figure, the average total delay T was 70 milliseconds, of which TPC occupied 80%. The second figure shows the breakdown of the delay. From the figures, the autonomous vehicle could receive the cooperative perception message within about 100 milliseconds in the worst case. The frequency of the point cloud measurement was 10 Hz, which was also the maximum frequency for the CAM. Therefore, it can be considered that the proposed system can deliver the message within the point cloud measurement interval and also within the CAM interval. We measure the PDR in the field test. We measure the PDR by comparing the LDM entries of the sender and receiver after the experiment. The figure shows the location of RSU and the driving route of the vehicle. The vehicle drove along the yellow line in the figure at about 3 km per hour several times within a total time of 1000 seconds. The color of the tile indicates the PDR at the location. A lack of tile indicates that no message was received at the location. It can be seen that in most cases, PDR gradually decreases as the distance increases. In addition, the building filters the message, leading to the sharp decrease in the PDR value. The results show that PDR is more than 80% when the vehicle is within 30 meters and has a line of sight to the RSU. Next is the research work about cooperative planning we presented 2 months ago. To do cooperative planning, we need to exchange future data. This is because today's cooperative ITS standards exchange only real-time information and there is no future data. Two representation formats can be used to represent and coordinate future data, grid-based and path-based, as shown in the following paper. At last year's VTC conference, an optional field called Path Future was proposed to extend the cooperative awareness message. Also, the research of maneuver coordination, a path-based future information exchange called planned trajectory was proposed. This research on the bottom right in the maneuver coordination research we presented at ITSC 2 months ago. We'll talk later. The contribution of this study is designing a roadside unit that enhances vehicles' prediction and planning cooperatively with other vehicles to improve traffic flow at intersections. The proposed method is divided into two schemes, a periodic message broadcast to exchange vehicles' future paths, we call it future path sharing, and a maneuver coordination algorithm based on the reservation table that manages the set of future paths in the RSU, we call cooperative planning. We implement the solution in Autoware. To the best of our knowledge, this study is the first to implement cooperative planning in Autoware. For future paths, first, we convert the trajectory to the future path. The trajectory consists of continuous paired sequences of the location and velocity. It results from the planning module's decision, and the control module follows the trajectory. The future path consists of continuous paired sequence of the location and time. The future path employs a data structure that makes it easy for cars and RSU to detect conflicts. The receiving vehicle can treat the received information as a dynamic obstacle by integrating it with the output of perception module. This integration potentially causes unnecessary deceleration because the future path is treated as a future obstacle. When RSU receives the vehicle's future passes and it updates its reservation table, the reservation table is the RSU database that stores the set of future passes sent by autonomous vehicles. When a received future path conflicts with other paths in the table, the RSU sends an initiation message to the vehicle to enter a coordinated mode. Our scheme is a hybrid one in which vehicle create a trajectory and RSU modify their speed along the trajectories. The autonomous path is calculated by autonomous vehicle to the desired destination. The coordinated path is a new path in which the RSU modifies the autonomous path to avoid conflict and improve traffic flow. We implemented the proposed method by extending Autoware. This figure shows the system design. Autoware provides the function of localization, perception, planning, and control. First, the trajectory sent from the planning module to the control module is converted into the future path and broadcasted 10 times per second via UDP. On the receiving side, the future path is merged with the result of perception. In this case, the future path will be recognized as a future obstacle, thus the vehicle may slow down unnecessarily. Therefore, the RSU generates a conflict-free path and performs coordination. Autoware planning module, which is divided into three parts: mission planning, scenario selection, and behavior planning. The mission planner calculates the entire route to the goal by searching the static map. A scenario selector decides which behavior planner should be used depending on the situation. Notably, it is technically challenging to have a unified behavior planner handle every possible situation. Currently, Autoware provides two, one for on-road driving and other for parking. We do not use parking module, and the lane driving module generates the autonomous path and send it to RSU by UDP at 10 Hz. Then RSU modify the speed of the path and return as the coordinated path. Here is the overview of our implementation. The white box comes with Autoware, and the blue box is newly implemented in our extension. Our extension is related to cooperative mode and a new behavior planner in the vehicle side called coordinated planner. On the RSU side, in addition to cooperative mode, we added the reservation table, conflict detector, and velocity manager. Here is the flowchart, and the detail is in the paper. The RSU apply one of the three modules for each vehicle as follows. Auto is used when the vehicle follows the autonomous planning mode. C-slow is used during the coordinated mode while slowing down, and C-fast is used during the coordinated mode while speeding up. We evaluated our implementation using the LGSVL Autonomous Driving Simulator. Three personal computers representing car A, car B, and RSU were connected to the LGSVL simulator. A wired network connected the three PC to LGSVL simulator. We choose a blind intersection pre-installed with LGSVL. We set the starting and destination points so that car A would pass through the intersection before car B in standalone mode as shown in the figure. We visualize a stationary vehicle as RSU. We evaluated the following scenarios. First, standalone autonomous car without communication. Second, future path only. Autonomous vehicle broadcasts the future path by V2V. Finally, future path with RSU, which is our proposed method, coordinated autonomous driving with RSU, including future path sharing. We conducted 10 simulation experiments, each of the three scenarios, using the same starting endpoints and destinations. The figures show the speed of two vehicles near the intersection. Green is the result of car A and orange for car B, and the larger value indicates the direction of the travel. In the standalone scenario, car B always stopped at 5 meters before the intersection for car A passing first. In the future path only scenario, car A and car B recognize each other sooner, so they slowed down within 20 meters from the intersection. The figure C shows that both car A and car B did not stop before the intersection using our proposal. The table shows all the results and passing times. In the standalone case, car A traversed the intersection first in all trials as designed. On the other hand, car A traversed the first 6 times in the other scenarios. The figure shows the passing time of the 10 trials and their variations. The future pass-only scenario slightly increased the average passing time for 2% because the vehicle slows sooner than the standalone, as shown in the previous slide. Our proposal, the future pass with RSU, successfully reduced the average passing time about 10 seconds, representing a 26% improvement. The coordinated path of the RSU effectively avoided conflict and improved flow. The last research work is maneuver coordination work we presented 3 months ago at ITSC. A vehicle recognizes the current position of other vehicle by CAM, but it cannot recognize that it is changing lane at the moment of lane change. Therefore, there is a possibility that one of the vehicles stops or slows down suddenly when the maneuver coordination message has been considered to solve this issue. MCM is still the middle of being discussed and the format of it not decided yet. Some researchers propose the MCM format including vehicle trajectory to cooperate in planning in the future trajectory of each vehicle. So our study proposed MCM meets several requirements such as robust against packet loss, bandwidth saving, handle duplicated instruction, and response to the abnormal termination or scenario changes. Also, we prototype the system and integrate it into Autoware. We explain the flow of proposed MCM in the situation mentioned earlier. In this figure, the red vehicle, the prescriber, will change the next lane, and it will collide with the blue vehicle, the receiver, and arrows show the planned trajectory of each vehicle. First, the prescriber decides the lane change. Then the state turns to the advertising, and the prescriber broadcasts the advertisement message periodically. When the receiver received it, it replies to the intention message, including the planned trajectory of the receiver to the prescriber. When the prescriber receives the intention, the prescriber replies to the ACK message to confirm the arrival. The receiver continues to send the intention periodically until it receives the ACK. After a certain period, the state turns to the prescribing phase. If the prescriber has received the intention, it detects the risk of collision with the receiver. If there is a risk of collision, the prescriber calculates the prescribed trajectory and sends the prescription to the receiver. When the receiver receives the prescription, the receiver verifies the safety of the prescribed trajectory. If the receiver follows the prescription, it sends the acceptance message to the prescriber. After that, the receiver follows the prescribed trajectory until the prescribed trajectory finished. It sends CAM periodically. So, if they cannot receive the CAM of other vehicle in certain time, they decided on the communication error and finished the scenario in the way. Finally, the prescriber sends the fin message at the end of prescribed trajectory and the scenario is done. Here is the strength of our proposal. First, it can save network bandwidth consumption and realize reliable transmission by advertisement and acknowledgement. Second, it can solve the instruction duplication issue by the introduction of the state. Finally, it can avoid the abnormal situation by sending the cancel message. Next, we explain the system architecture of MCM. We designed the architecture that can be used for various situations such as lane change and intersection and lane merge. Therefore, we separate the function commonly required for maneuver coordination as MC service and the function required individually as MC application in order to correspond to each scenario or application. Then, we implemented the MCM system for autonomous driving. We integrated two open source software, OpenSys and Autoware. This figure shows the architecture of our implementation. In this presentation, I skip the detail of the implementation. We evaluated our implementation with a planning simulator built in Autoware. We show a test driving demo and result of communication bandwidth and the impact of MCM on traffic comfort. Also, we did the test drive in the lane change scenario with 2 vehicles and 4 vehicles. This shows a visualization of Autoware information with Rviz. The prescriber changed the lane and the other 3 vehicles at the target lane. You can see that prescriber select the receiver B in this and the receiver B slowed down in advance before changing lane to get the proper distance. Next, we investigated how much MCM impact to the traffic. We measured the time it took for the receiver to arrive the destination about 260 meters ahead when traveling at 30 km per hour and at 50 km per hour. First, in the MCM, we can see that the arrival time is reduced in both cases. Furthermore, the arrival time is shortened by about 5 seconds at 30 km per hour and about 7 seconds at 50 km per hour. It indicates that the faster the speed is, the greater the effect of MCM is. Finally, we measured the change in arrival time when the packet loss rate was changed. This time, we measured the arrival time at the message timeout of 0 seconds, 1 second, and 2 seconds. This graph classifies arrival time into 29 seconds or less, 29 to 30 seconds, 30 to 31 seconds, and 31 seconds or more, and shows them as percentages. The graph shows that the arrival time is increasing rapidly as the packet loss rate increased. It can be seen that the arrival time increased sharply from 10% at t equals 0, 60% at t equals 1.0, and 70% at t.2 seconds, according to the study in the reference. That conducted a practical evaluation of V2X, the packet loss rate is under 20% in the line of the sight. This result reads that this method has some robustness against packet loss when t equals 1 or 2 seconds. In this talk, we talked about the intersection of 3 fields in connected cooperative automated mobility. Next, we explained the technical standards, especially in Europe, and described Autoware, a popular open-source automated driving software. After that, we introduced 3 recent research work in our laboratory on V2X assisted automated driving. Suppose you are interested in learning more about each of these studies. The articles and presentation video are now available for open access. Future directions include large-scale experiment, validation in digital twins, and deployment. We are participating in the Cool4 project this year. This project is conducted by a consortium consisting of the University of Tokyo, Nagoya University, National Institute of Advanced Industrial Science and Technology, and Mitsubishi Research Institute Inc. This project aims to achieve Level 4 autonomous driving services in diverse areas using a cooperative system by 2025. It also creates a testbed area where the most appropriate cooperative system is adapted to local characteristics such as road environments and traffic situations. We promote a cooperative systems implementation under local characteristics based on analysis and study of regional use cases. Also, our team develops business models for data exchange schemes that also benefit other types of mobilities. This is the end of the talk. Thank you.